So this is the review for Unit 7. We're dealing with exponential and logarithmic functions. So the first thing we're going to do is consider the function f of x equals 3 to the x power. We're going to make a table of values for this and graph it. So if you raise 3 to the negative 2 power, you'll get 1 over 9. Okay, now if you put that in your calculator, you get some kind of decimal, but they convert the decimal to a fraction. All right, 3 to the negative 1 gives you 1 over 3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. So if you plot this on our graph, negative 2 and 1, 9 is like there. Negative 1 and 1/3 is there. 0 and 1. 1 and 3. And 2 and 9. So your graph should look something like this. Now we can see that it's a growing, so it's a growth function based off the graph, but we should also know that it's a growth function because the base value is greater than 1. So that means it's an exponential growth. Now if we want to make a table of values and graph the inverse, which is over here, I don't like these numbers here, so I apologize, but they should not really be there. What you're going to do is you're going to take the values you had from x and y over here and then put them over on the other side, but flip them. So the y becomes the x, and the x becomes the y. So you have 1 over 9 and negative 2, 1/3, negative 1, 1, and 0, 3, and 1, 9, and 2. So those are your inverse values. If you put these on your coordinate plane and graph them, you have 1/9 and negative 2, which is like there. 1/3 and negative 1, which is about yay. 1 and 0. 3 and 1. And 9, 2. Your function looks like this. And that's the exponential function. Oh, sorry, that's the inverse of your exponential function. So it's a logarithmic function. Okay. So now let's look at the characteristics for these two functions. We're going to go back and forth looking at the graph and this table here. Okay, so I hope you don't get motion sickness. So your domain for this graph, for the f of x function, our domain is everything. Okay, there's nothing that it cannot be. So would it be negative infinity to positive infinity? Now for the other graph, the inverse, that's not the case. Okay, the graph does not go past this y-axis. I'm going to put that in red. For a very good reason. Okay, so this graph does not cross that boundary line of the y-axis. So that means its domain is going to be from 0 to infinity. Notice the 0 has a parentheses because the graph does not actually touch the y-axis. Now for the range, in the first graph, the f of x graph, the graph starts at 0 and goes up towards infinity. It does not go past this boundary, which is the x-axis. Okay? So it's going to go from 0 to positive infinity for the range. Now for the inverse, the range, it goes, as it keeps going down here, and it's going to go to the right and up over there. That means that its range is going to be from negative infinity to positive infinity. Okay? Nope, I didn't change it back to blue. That's okay. All right, next the asymptotes. So this boundary line for the f of x function that I drew over here on the left, that is also your asymptote. And that equation is y equals 0. On the other side for the inverse function, that boundary line is on the y-axis, which means that boundary asymptote is x equals 0. Let me turn back to blue. I like blue better. Okay. X-intercepts. All right, the first graph does not cross the x-axis. It doesn't actually touch the x-axis, so there are no x-intercepts. Okay? But on the inverse graph, it does cross the x-axis at 1, 0. The y-intercept. The y-intercept for the first graph, it does cross the y-axis at 0, 1. But since the y-axis is the boundary line, the asymptote for the inverse, it does not have a y-intercept. Okay? We got two more things. Intervals of increase and decrease. Well, this graph is going up. It is increasing. Over the entire domain. Okay. Now the inverse graph is also increasing. Now, we could say entire domain, but I'm going to be a little more specific because the entire domain for the regular function is from negative infinity to positive infinity. I'm just going to say it's going to be increasing over from 0 to infinity. I'm going to list its domain. You could probably say entire domain, and it wouldn't be wrong because the entire domain is 0 to infinity. But I'm going to put it as an interval notation there. I think that's a little more specific because that domain is restricted to begin with. Okay, the end behavior. Okay, so here we go. As x goes to the left towards negative infinity, what is the graph doing in the first function? Well, the graph is over here, and it's going closer and closer to 0, but it will never get there. So that means we're going to put down it's going to be approaching 0. As the graph goes to the right towards positive infinity, it's going to be going up towards positive infinity. Okay. As we look at the next graph, as the inverse graph goes to the left, but as that graph's going to the left, it's going towards 0. Okay, it's not going to hit negative infinity because it can't get past the y-axis. Okay, that means the graph, as it's going towards 0, is going towards negative infinity as it goes down. Okay, now on the right side, it's going towards positive infinity. Okay, and as the graph is going to the right, it's also going up towards positive infinity. And those are your characteristics. Okay. Look at the same idea, but this time with a decay function, because our base value is greater than 0, but it's less than 1. So, if you raise 1/3 power to the negative 2, you get positive 9. To the negative 1, you get positive 3. To the 0 power, it would be 1. To the first, be 1/3. The second, be 1/9. Okay, so this function will look like this: 2 and negative 9, or sorry, 2 and positive, negative 2 and positive 9. I'll get it. Negative 1 and 3, 0 and 1, 1/3, 1/9. So it's going down. Okay, if we do the inverse, I'm going to get rid of these values here because we're going to replace these. We're going to flip the x and y terms just like we did for the previous one on the next graph. So you're going to get 9, negative 2. Oops. You're going to get 3, negative 1, 1, comma 0, 1/3, comma 1, and 1/9, comma 2. So 9 and negative 2. Right there. We have 3 and negative 1. We have 1 and 0. We have 1/3 and 1. 1/9 and 2. So your function looks like this. Okay. Now we're going to look at the characteristics again. So for the domain, the original function, the original decay function, is got no restrictions on its domain. It's from negative infinity to positive infinity. On the other function, though, it has a restriction because as it starts off, there's that boundary line of the y-axis again. Okay, so that boundary there means that the domain is going to start at 0 and go towards positive infinity. For the range, these are basically reversed. Okay, so for the range, this first graph, let's make our boundary again, is again bounded by that asymptote on the x-axis, which won't allow it to go down below 0. It won't actually allow it to touch 0 to begin with. So our range is going to be 0 towards positive infinity. So it's just going up from 0 to positive infinity. The range for the other graph is negative infinity to positive infinity because there's no restrictions on what y can be. The asymptotes are the same as the above graph. So the first one is y equals 0. For the inverse, it is x equals 0. Those are those asymptotes, those red dotted boundary lines that the graph cannot cross. The x-intercept for the first graph, there is none because the asymptote is on the x-axis, which means there cannot be an x-intercept. The other graph, the x-intercept is 1, 0. So it goes through the x-axis. For the y-intercept, you have 0, 1. So it goes through the y-axis. For the inverse function, there is no y-intercept because that's what the asymptote is on, the y-axis. Intervals of increase, decrease. Something happened to that little chart thing. All right, this graph is decreasing because it's a decay function over the entire domain. Okay. The other function is also decreasing, but we're going to restrict what its domain looks like because it's not over from negative infinity to positive infinity. It's still decreasing over 0 to infinity. Excuse me. Finally, end behavior. As the graph goes to the left towards negative infinity, what is it doing going up or down? It's going up towards infinity. As the graph moves to the right towards positive infinity, the graph gets closer and closer to 0, but it never actually gets there. For the inverse function, as the graph moves to the right, to the left, it's going to only move to the left on this inverse up until it hits that y-axis asymptote, which means it's really not approaching infinity, it's approaching 0. Okay? The graph is going up towards positive infinity. As the graph moves to the right towards positive infinity, what is the graph doing? The inverse, as it's going to the right, it's also going down towards negative infinity. Okay. All right, converting logarithmic and exponential equations from one to the other. Okay, so again, this is your base. This is your exponent. So if your base is 3, that means it should be log base 3 of 27 equals x. Okay. You have log base 1/3 of 27 equals x. Here you have log base 2 of x equals 7. And then finally you have log base 27 over 3 of 5/9 equals x. So that is converting an exponential to a logarithmic. You should be able to see the pattern. The exponent is always the answer at the end. The base of the exponent is the base of the log. Okay. All right, same idea, but you're working backwards now. So I've looked at this a couple different ways. If we get rid of the log, the base becomes the base of this exponent. So we have 3 to the 8th power equals 6,561. All right. Base of 5/9 becomes exponent of 4 equals x. All right, now if you don't have a base that's listed, like right here, we don't have a base next to the log. I talked about this before in the notes. The base is automatically then 10. So this is going to be 10 to the 4th equals x. Get rid of that log. The base comes over to the other side. It's a 10 because it's not listed. Equals x. Also in the notes we talked about natural logs. Natural logs automatically have a base of e. So you get rid of the natural log. The e becomes the base of the exponent x, which equals 6. Okay. Let's look at some transformations of these exponential functions. we have two transformations here. We have -1 and -4. Okay. So let's describe how it's going to transform everything first, and then we'll get into the function, and so then we can get into the graph, and then look what the graph looks like when we transform it. Okay, so the -1 is going to be a horizontal shift. Since it's negative, it's going to go to the right by 1. The -4 is a vertical shift. Since it's negative, it's going to go down by 4. So what we're going to do is we're going to take our points that were given in the graph here and make them go to the right by 1 and down by 4. So this first point goes 1 to the right, 1, 2, 3, 4. 1 to the right, 1, 2, 3, 4. 1 to the right, 1, 2, 3, 4. So our whole graph got moved that way. So we just take each point and move it based off of our shifting. And that's it. Okay. Next one, we again have two shifts. We have +7 and +9. So it's a horizontal shift. Since it's +7, it's going to go to the left by 7. +9 is going to have a vertical shift. Oops. It's going to go up by 9. So again, we're going to take our points and move it left 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 7, 8, 9. And move it up by 9. 2, 3, 4, 5, 6, 7. And move by 9. And then right there. So that's what our graph should look like. Let's get rid of this little dot there. Some of these little dots. Okay. So our graph would look something like this. And there's your transformation. All right, last section of the test or the review sheet is the solving these equations. Okay, for the first one, we're trying to, we can see we have 2x to the third minus 50x. Well, 2 and 50 share a common term, it's 2. And x cubed and x share a common term with x. So we take those two things out, we're left with x squared minus 25. Now what's inside the parentheses should be familiar. It is a difference of two squares. It is x plus 5 times x minus 5, and you factor it. We still have the 2x out in front. Now that it's completely factored, we set each one of the factors equal to 0 and solve for x. So we have x equals 0, -5, and +5. Those are your answers. Here, these should look familiar because we just did one over here. Again, difference of two squares. X squared minus 49 is going to be x plus 7 and x minus 7. X squared minus 9 is going to be x plus 3 and x minus 3. If we set all those things equal to 0 and solve, we're going to get -7, 7, -3, and 3. And there we go. All right, now we have some radical equations from the last unit. To solve this, we have to get the square root part by itself, which it is currently not because there's that -x right here. So we're going to add x to the other side. So we have the square root of 6x minus 5 equals x. Okay. Now that it's by itself, we can square both sides to get rid of that square root sign. We have 6x minus 5 equals x squared. Now we take the stuff on the left and bring it to the right because I don't want to make my x squared into a negative by subtracting it. So I'm going to subtract 6x and add 5. The stuff on the left goes away. We have x squared minus 6x plus 5. Okay. Now we can factor this. What are the factors that make up 5 when you multiply two numbers but add up together to give you -6? And they would be -5 and -1. All right, negative 5 times negative 1 is positive 5. Negative 5 minus 1 is negative 6. So our answers are x equals 5 and 1. But this is a radical equation. We've got to check these answers. So if we put 5 in for x, we have 6 times 5 is 30. 30 minus 5 is 25. The square root of 25 is 5. And 5 minus 5 is 0. So that checks out. Actually, put in 1. 6 times 1 is 6. 6 minus 5 is 1. And the square root of 1 is 1. 1 minus 1 is also 0. So that works. They both work. Going over to the other one. Again, we have a radical equation. We have to get the square root sign by itself first, which means I'm going to add the 9 to the other side. So I have the square root of negative x plus 6 equals x plus 6. Now that the square root sign is by itself, I can square both sides. The square root and the square root will go away. I'll be left with negative x plus 6 on the left. On the other side, I have to square x plus 6, which means I have to multiply x plus 6 times itself, just like that. So x times x is x squared. X times 6 is 6x. Another x times 6 is another 6x, and 6 times 6 is 36. All right. I'm going to add x and subtract 6 from the left to the right. Those will go away, and I combine all my like terms on the right-hand side. So I just have x squared. 6x plus 6x is 12x plus 1x is 13x. And then 36 minus 6 is 30. So two factors that multiply to give you 30 but add up to give you 13 are positive 10, positive 3. So x will equal negative 10 and negative 3. Excuse me. Again, you got to check your answers for these problems because it is a radical equation. Okay, so negative 10 in for x gives you negative and negative 10 is positive 10. Plus 6 is 16. The square root of 16 is 4. And 4 minus 9 is 5. So we have 5 on the left. Negative 10 minus 3 is negative 13. Oops. And that is not a true statement. So negative 10 cannot work. Putting in negative 3. Negative 3 in for the x. Negative 3 times negative 1 is positive 3. Plus 6 is 9. The square root of 9 is 3. 3 minus 9 is, let's get rid of the top part. 3 minus 9 is negative 6. Negative 3 minus 3 is also negative 6, and that checks out. That is correct. So negative 3 is the only answer that does work. And that brings us to the end of the review. If you have any questions, please reach out to me and ask. Otherwise, good luck on the test starting Thursday, and you have until the end of Friday.